Okay, so let's begin our second lecture series. Okay. So this lecture series is about like showing that showing that the universal holomorphic covering of the holomorphic universal covering of the potential disk is the exponential map. Okay, so that's the goal for this lecture series. And okay, so I will okay. Okay, so basically I will tell guys later about the textbook that I'm referring to. Okay, so I'll ask Guy. Yeah, okay. So anyway, so let's start with the lifting theorem in the covering space. Okay. So theorem. Okay. So let gamma from this x hat to x be a connected covering space of a connected topological space X. Okay, and then we let this X naught to be a point in X, and then we let this X naught hat to be one of the pre-image on the gamma. Okay, so let's first prove the path lifting property. The path lifting property says, so if gamma from a b to x is a path in X with gamma of A is equal to X naught, then there is a unique lifting this gamma hat from this AB to this X hat of gamma to a path in X hat with gamma hat of A is equal to hat X naught. Okay. Okay. So yeah. Okay. So let's prove the result for this path lifting property. we first prove the uniqueness. In part A. Okay, so suppose this gamma ux is a path, and we have this gamma of x naught hat is equal to x naught, which is gamma a. So suppose we have a path, gamma AB is a path in X, where path is just a continuous band from this closed interval AB to this X. Okay, so and then gamma of X, where so this X hat, wait a second. Gamma AB in X is a path in X with gamma A is equal to X naught. So yeah, so X naught is like the starting point of this gamma, right? Then there is a unique lifting from this gamma hat of gamma to a path, where okay, so this is like the lift, right? So and wait, did I commit something wrong here? Okay. Sorry, maybe I think I made a mistake here. So let me check. Okay, sorry, my bad. So, yeah, so this is like, okay, so I think, yeah, so here we use the current projection is like the big, I'm not sure how to pronounce this letter really. So, let me, yeah, I'll check afterwards. So let's call it big gamma, okay? Because it just looks like big gamma. I don't know the exact name for this one. Sorry. So, okay. So the current projection of this x hat, which is equal to x naught, is equal to Rn. Okay. Okay. As in part A, and then so we have for any evenly covered. Neighborhood. Okay. Okay, maybe I should split up more. Okay. So here, so neighborhood U of x naught. It is clear that if this gamma, okay. So yeah, sorry, I think I really like R, but yeah, let's call this R, okay, and let's call this math gamma, okay. Sorry about my previous pronunciation. Okay, so let's just do that. Oh, this R is a path, okay. And then we call this gamma the covering space projection, which is equal to R of A, okay. So it's clear that if this R, if R lies in U, okay. If R lies in U, then there is a unique listing of R with initial point x naught hat. Okay. So why it is true? So basically, so U is a evenly covered neighborhood. That means you have this but yeah, so we have this gamma inverse of U is equal to the disjoint union of sorry, I forgot the index. So I think the index should be okay. Let's call this U alphas. So some alpha is some index set. Okay. Where and then this gamma restricted on this U alpha is a whole homomorphism onto this U, right? Okay. So why it is unique? Because if you take any point, okay. So if you take any point, let's say, okay. So this x is a okay. Where am I saying? Okay. So we know that this x naught hat is that's in gamma inverse of U. Okay. Where am I saying? Okay. So because we know that this gamma hat of x naught is equal to x, right? And then this x is in U. So therefore, this x naught hat is contained in the inverse image, right? So the thing is that then it must be contained in one of these sets, okay? So then, so just pick, because they are disjoint, right? So just pick any, like, it cannot be contained in the other set. So basically, there must be a unique U alpha that contains this x naught hat, okay? So for that unique U alpha that contains this x naught hat, wait. Okay, so why there's a unique? So, okay, so let's say that so we have this u let this u alpha hat to be the unique to be the unique to be the one of the alphas that contains the x naught, right? So x naught hat, sorry, yeah. So then what happens? So then what we want is that we want to construct, we want to show that there's a unique lifting. Okay. So basically, it's easy to see that there's a lifting, right? So basically, you can say that because this is a homomorphism, so therefore you just inverse compose the map, right? So it's just like you let the map to be this gamma restrict on u alpha inverse. So let's see where the compose goes. So we want a map from this where? So you want a map from this you want to get a lifting, right? So basically you want to get a map from this AB to upward, right? So you want to first do gamma and to R, sorry, and then do this reverse image. So basically what you want is that you want to first do R, and then second you do that. Okay. So okay. So why it is unique? Because if you have another lifting, right? So let's say that you have another lifting. So then okay, so let's see. So that this maybe so okay, so it's a lifting. Right, because yeah, because yeah, because it's continuous, right? Yeah, and then the projection of this map is the same as yeah. So if you project it down, yeah, it's the same. Okay, okay. So let's see why it's unique. So if you let this gamma hat to be another x hat, I lift such that this gamma hat of x of A is equal to x naught hat. Okay. So why it is true? Because what I want to say. So I want to say that if you do the projection and then they must be the same, right? So what I say is that why it must necessarily stay in U alpha, right? So I want to say that this map stays in U alpha. So because okay, so then so why it necessarily stays in U alpha? What were U alpha tilde? Sorry. Okay. So if the path does not stay inside U alpha tilde, then Okay, okay, I see. Okay, so that's the argument, I see. Okay. So, sorry, I'm in a awkward position that I'm out of space. So, let me just write it here, maybe. Okay. So let me write the argument here. Okay. So, if let's see, okay, so, okay, let's say this way. So if this image, sorry, what do I want to say? Okay, so gamma tilde. Okay, let's use gamma tilde to avoid some confusion because this X is like the covering space notion. So wait. Oh, okay. Okay, there's so much notation. So let's just call this tilde. Anyway, let's call this R tilde to be the listing. Okay. So if this R tilde of this AB, the image set, lies in what? Lies in where? U alpha tilde. Okay, so where is like the upstairs? Then, because it is a homeomorphism, right? So then, okay, what do I say? Okay. So then, we have the gamma of composed with R tilde. Sorry, I think I did again. Okay, this is the gamma. This is R tilde of let's say T, which should be the same as RT, right? Okay, so this is by definition. Okay, and then implies, because this image lies in U alpha, so therefore this one is equal to the same as gamma restricted on this U alpha tilde, right? Of yeah. Okay, it's equal to gamma. Okay. So then, so what do I say? So I want to say that, okay, I want to say, okay. So I want to say that this gamma is gamma AB lies in U alpha, then they should be the same, right? So okay, so then so this implies that take the inverse composed with this gamma of u alpha tilde composed with gamma t, right? So if you compose with the inverse, which would be the same thing as u gamma, oh sorry, RT, yeah, RT, and then inverse of composed with RT, which is the same thing as the thing that we stated there, right? Okay. So let's call this R hat. Okay. 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 Yeah. So then that gives you the left hand side is exactly the R tilde t. Okay. All right. So I think that's the okay. No, not yet. Okay. So if okay. So otherwise, okay. Let's see what happens next. So if this R tilde does not lie inside this U alpha, so then what would happen? So okay. Sorry, I have to erase it. Okay, so now, okay, so that's case 1. Okay, case 2. So if the image does not let's use this notation for does not contain in U alpha. Okay, so that means okay, so this implies because okay, because okay, so this implies there exists some other element, right? So what do I want to say? So you know, so okay, so since okay, so we know that this gamma of AB is contained in gamma sorry, RAB is contained in this gamma inverse of U, right? Because this R of AB is inside U, right? So and then therefore the idea is that since it's contained in gamma inverse U, which is the disjoint union of the open set U alpha. So therefore, if it is not contained in this U alpha tilde, then we know that there must be other set in this disjoint union other than the U alpha that contains that such that this R of AB is contained in those U alphas. So then this R tilde AB must be the disjoint union of those open set, right? And remember that this AB is continuous, set, right? And we know that the image of a continuous set, connected, right? Because, yeah, and then we know that the image of connected set is also connected, right? Wait, why am I confused? So you take the image of a connected set. Suppose there's a separation into of the image set into AB. Then okay, okay. So suppose that the image is equal to A disjoint union B. Then Y the pre-image is the disjoint union. So if you take the pre-image of a set A, then okay, some set of X, that's okay. And then you take the, oh, I see. If you take the pre-image of B, then okay, the pre-image of B is now okay, cannot be contained. Okay. Okay. Okay, so I think the continuous map of wait, we should have okay, yeah. Yeah, so basically, yeah. What's the okay. Okay. Oh, okay. Okay, yeah. Okay. Yeah. Okay. Yeah, so since the image of the connected set is connected, so and then we know that this is the disjoint union of some other open set. Okay, so therefore contradiction. Okay, contradict with that the image of open else. Sorry, of connected set is connected. Okay, yeah. Okay. because what's the definition of preimage? Oh, okay, it's the set of all x. Okay. The definition of image is the set of all x that gamma x. Yeah. Okay. Okay, and then okay. Okay, I think it's true. Okay. Because yeah, because this set is contained in Y's because gamma of AB is in where? Gamma of AB is in oh, okay, because okay. 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 Okay, so why is it okay? Okay, what else? Why is it contained in some destroyed unit? Okay. Okay, so we know that it is contained in okay. okay, yeah, because it composed with the projection and then it like you okay. Okay, because if you take any x, okay. Okay, because you take any. Okay, okay, I see, okay. Okay, because take any x. Okay, we know, okay. I see, okay. 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 Y, okay. So now Y is the disjoint union. So, so Y is the disjoint union. So, so if you take any x, okay, I want to say that this is equal to some disjoint union of U alpha, right? So why is that? So, okay. So, compute this one. So, x is in, okay, I see, okay. And then ys is, okay. Yx is in that because you have this okay, I see. Okay, never mind. Okay, so this is so this is contained in that, and then but why this gamma of AB is contained in I want to say that this is equal to okay, I want to say that this is equal to some disjoint union, right? Yeah, sorry, I just make myself some yeah. Okay, so this is equal to the disjoint union, okay. So I want to say that it's equal to the disjoint union of some like some set. Okay. Wait, what's the definition of connected? So if you take okay. So okay. You get that, and then what happens if you want to say that? I wouldn't say that this is wait, it's not necessarily equal to, but okay. So let's first assume that it's contained in this disjoint union. So y is true. So wait, I don't even need that because because definitely this U alpha contains this set, right? And then this union of this U alpha, and then another set is the set where but the question is, can I do that? I want to say that this alpha in this set take away this alpha tilde. So, oh, okay. I think we are able to wait. What's the definition? Okay. I think we will be able to define and then what? Okay. I think we will define. Wait, why am I confused? So. Okay, I think. Yeah, we'll be able to. Wait. Okay, so y is the disjoint union. So if you take. Okay, yeah. Wait, so if you okay, yeah. So we'll be able to okay. So let's see. You take the disjoint. So what's the definition? So how do you even define? Oh, okay. I see. Okay. I see. Okay. Yeah, because these sets are all destroyed, right? Because wait, why they are okay? Because these are destroyed. Okay, because these are destroyed. Wait, why these are destroyed? So if you have okay. Yeah, so these sets are all wait, why? Okay, these are all. Why am I confused? So why they all destroyed? So if you take okay, okay. So what do you mean by index? Okay. So what's the definition of destroying? Let's see. Okay, let's see. So here, okay. So what's the definition for? Okay. Destroy union. Then. Okay. some alpha. What's the definition for union? So what's the definition for arbitrary union? Okay. Set of x. X is in for some alpha. Okay. Okay, I see where I get stuck. Okay. Okay, so I think I need to check the definition for, I think this is like alpha in itself, right? So, and then what's the definition for destroyed? So, okay, so these set are destroyed. Okay. Okay, I see. Okay, I see. So, okay. All right, so I think this is the proof, right? Because, yeah, the other side is not empty, and then this is contained in the disjoint union of these two sets, right? And then what happens next is that you may have the wait. So for connectedness, do you have the set to be also contained in the ambient space? Okay, 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 yeah. So I think the case is that I think in order to be strict, if you want to have this one. I think this will finish the proof. Okay. Okay. Because, okay. Sorry, I always mess this around. Okay, so yeah, so it's connected. So in what sense? Okay. So okay. So if the image of a connected set is connected, so okay, the continuous, okay, I see, okay. So onto what space? That's the question. The image of a connected set is connected. So it's a continuous map, okay. Oh. I think you need to specify the topology. So what's the topology? What is the topology? What is the topology? So we have a function that maps x to y. subspace. Oh, subspace topology. Wait. Okay. Okay. I think you need the, oh, you don't need topology actually, or do you need? Okay, so this has topology. The image, oh, I see. So, the image is a topology. Okay. Is it? Okay, what's the topology? Take the inverse image of only open set in the image, then okay. 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 Image of connected set like this. This is the topology. Could there be any other topology on it? Could there be any other topology? The topology is given by, so if you consider the image set, which is, wait, what is the definition for image set again? Okay. And then and then I will define the topology of this function to be the set of all so here y, okay, so y is so what's the definition for the image? Okay. is there could be some other I think there could be some other way. So in one topology, right? In one topology. Topology. It is a topology. Okay. So let's see whether it's a topology or not. So let me see if the time is up. All right, so I think the time is up now. So sorry, yeah, I'll stop here. Yeah, and then we can continue next time.